Okay, let's talk about some special matrices. We have just some of them. Diagonal matrices, triangular, symmetric, symmetrical, nilpotent matrices. Okay, so diagonal matrix. It's easy to remember. All the entries in the off diagonal, or the entries that are not diagonal entries, are 0. Here's an example of the diagonal matrix. And if we'd like to define a diagonal matrix using index notation, we would say that a diagonal matrix is one whose ijth entry is either 0, right? Well, what is it defined by? The entries are 0 if I does not equal j. So the diagonal entries are exactly those ones where the row and column index match, right? So this is the 1, 1 entry, 2, 2 entry, 3, 3 entry. So this is the way we define the diagonal matrix. If we're not in the diagonal, so I is not equal j, then the entry must be 0. Now these have some diagonal matrices have some convenient properties. For example, if you raise the diagonal matrix to a power, let's just label these. These could be 0, by the way, right? In the diagonal matrix, these diagonal entries could be 0. But if you raise the diagonal matrix to a power, you can convince yourself that's the same as raising each diagonal entry to that power. So it makes computing powers of diagonal matrices simple. It's a useful property. Okay, another property we want to use is the fact that if you want to invert a diagonal matrix, assuming it's invertible, you simply take the reciprocals of the diagonal entries. You can easily check by multiplying matrix A with its inverse, and you'll see that you indeed get the identity. Okay, so is this diagonal matrix invertible? No. So the lesson here is that if you want to find the inverse of the diagonal matrix, you need to take reciprocals of the diagonal entries. Those diagonal entries better not be 0 if the matrix is to be invertible. So this doesn't have an inverse. Okay, so let's do an example. So suppose this is a diagonal matrix A, and we want to find a matrix B, whose which b to the -5 is equal to A, say. So let's find matrix B such that b to the -5 is A. So of course by this we mean b raised to a power 5 and its inverse gives you the matrix A. And what we can do is, well, just make sure we think of it that way, because what does it mean for a matrix to be raised to a negative integer power? Well, it's this. Or equivalently, it's the inverse of b raised to the power 5. Now, why are we going to take this point of view and not this one? Well, because if I wanted to solve for b here, I would have to, if these were numbers, I would be taking the 5th root, right? The 5th root. And in general, the roots of a matrix are not defined. For a diagonal matrix, it is, because you can just take the 5th roots of each diagonal entry. But I'll be more formal. I'm going to take this approach. So if I want to undo the inverse, what do I do to both sides? Invert, yeah. Inverse of an inverse. Now I get b to the 5 power. And here we are inverting a diagonal matrix. So we know that's simply the reciprocals of the diagonal entries. Reciprocal of -1, -1. Okay. So we found the inverse of the diagonal matrix. So now we can imagine that B can be diagonal, correct? So we would have B1, B2, B3, and zeros everywhere else. It's possible that I could find, is it possible that I could find a non-diagonal matrix? I don't know, I don't think so. But of course, because I'm assuming B is a diagonal matrix, I can go ahead and compute this power by simply raising each entry to the power 5. Okay, so we would have B1 to the power 5 has to equal to 1 over 32 for these matrices to be equal. The second diagonal entry to the power 5 has to be -1. And B3 raised to the 5th power has to be -243. And what is the, now we can take the roots, the 5th roots of our numbers here. So what's the 5th root of 32? So the 5th root of 1 over 32 would be 1/2. And the 5th root of -1 is -1. -1 to the power 5 is -1. And what's the 5th root of 243? Negative, yeah, so -3. So indeed, we are able to find the matrix B, which raised to the power of 5 and then inverted gives you the matrix A. Another application of symmetric matrices that is in your homework is this little problem where we're supposed to find a diagonal matrix C. So you're given a diagonal matrix, right? So let's make that, doesn't matter, 1, say -1, just for illustration's sake. So this is a matrix, a diagonal matrix, and we want to find a symmetric matrix C such that C plus its inverse gives you A. And so the setup here would be, well, I know C is symmetric, so, and it has to be 3 by 3 because A is 3 by 3. So I can just come up with a generic and just put some entries here. 0 everywhere else. And then we know that the inverse of this diagonal matrix would have reciprocals. Two diagonals here. And we would like that to be equal to the given matrix A. And how do we go about finding this matrix C? Well, hopefully it's clear that when you add these diagonal matrices, you're going to get C1 plus the reciprocal of C1 has to give you this number 1. Right? And looking at the next diagonal entry, you get a similar equation. and then we can solve for C1, C2, and C3. Okay. Like so, in the first equation, for example, let's just multiply everything by C1. So now the solutions we might get might not be real numbers, right? This is a quadratic, and it's not guaranteed that this quadratic has real roots, right? So I'll just use quadratic formula here. So minus b is 1 plus or minus square root of b squared minus 4ac. So I'm using quadratic formula divided by 2a, and I'm getting complex numbers. Okay. And I would get complex numbers for the second equation as well. So whether such a matrix exists depends on whether we're going to allow complex entries in our matrix or not. So that's a question for your professor. Am I allowed to use complex entries from the matrices, or are we restricting ourselves to real valued matrices? Yeah, matrices with only real entries. So if you're not allowed complex entries, the answer to this question would be there is no such real symmetric matrix, right? But there's only a complex one with complex entries. I believe this would give us a real root though. Again, I'm going to multiply both sides by C3 to get a quadratic. And according to the quadratic formula, C3 would be negative b plus or minus b squared minus 4ac divided by 2a. So I get that C3 would have to be 1. And that's real value. That's a real value answer. And so I don't know how you would answer this question in your homework if you have complex entries. You have to ask your professor or TA. We can come back to number 2 in your homework, because it's really a throwback to the previous material. So let's continue to something like number 3, which is an interesting problem. Number 3. So we can So does anybody know the binomial expansion for something like a plus b raised to the power n, right? So a plus b squared. Okay, so a and b are numbers. They're real numbers. If you expand this, you get a squared plus 2ab plus b squared. And if you have a plus b cubed, you have a cubed 3a squared b plus okay. And you can continue this game, but there's a pattern here. Yes, it is. Right. So if I do say a plus b to the 1, okay, to the 4th. So on. Okay. So the idea here is to capture a formula to give you a formula that captures this pattern, and that's called binomial expansion. Binomial, I guess, because there are two terms here, and we raise this to an integer power n, or positive integer power n. And we would write that this is the sum as k goes from 0 to n. And then we have this choose function, binomial coefficient, n choose k. We have a to the k times b to the n minus k. And this formula captures this pattern where this choose function is defined in terms of factorials. It's n factorial divided by k factorial divided by n minus k factorial. So, for example, a plus b to the power 4, according to this formula, would be the sum as k goes from 0 to 4. 4 choose k, that's n choose k. A to the k times b to the 4 minus k. If I write this out, you start the index at k equals 0, so the first term reads like 4, choose 0, a to the 0, b to the 4. And then the next term is when k is 1, and then when k is 2, and so on. K is 3, so 4 choose 3. And finally when k is 4. Here's the stuff. All right. And if I were to compute these, okay, so I guess I should mention what is factorial if you haven't seen it before. So 2 factorial is 2 times 1, 3 factorial is 3 times 2 times 1. So I guess in words, n factorial would be the product of the first n consecutive positive integers. And it's easier to spot the pattern than to articulate the definition. And 0 factorial is defined to be 1. It makes stuff work out. So if I want to compute these, 4 choose 0, for example, according to this definition, is 4 factorial divided by 0 factorial, and then 4 minus 0 factorial. And recalling that 0 factorial is defined to be 1, and 4 minus 0 is 4, you see that you don't need to do any computations because you have 4 factorial divided by exactly 4 factorial. So the first term, the first binomial coefficient is 1. And 4 choose 1, you compute as n factorial divided by k factorial divided by 4 minus k, or n minus k factorial. 1 factorial is 1, and then we have 3 factorial. So you note that if I were to write this out, I shouldn't have bothered, right? Because this is 4 factorial, this is 3 factorial. You see that both 3 times 2 times 1 is both factors, so we just get 4. And I'll do 4 choose 2, but you see the pattern. But you just want to be familiar with the formula to do the assignment. So you have 4 times 3 times 2 times 1. And 2 factorial is 2. 2 factorial is 2. So it gets 6. And you're right. If you're familiar with Pascal's triangle, these binomial coefficients are generated in Pascal's triangle. But you would get exactly what you wrote down. Well, not exactly, in reverse order, right? There's some symmetry here. All right, so the question is, does this binomial expansion hold for matrices? The answer is that in general, no, right? Not in general. So we don't have such a thing for binomial, for matrices. And why would that be? Well, let's just try to recall when we compute, say, matrix A plus matrix B squared. We said that when you multiply this out, right, since matrix multiplication is not commutative, you'd have to keep the order of multiplication correct. So you would have A times A, then you would have A times B in that order, yeah. A is multiplying B from the left. Then you would have B times A, and then you would have B times B. So it's B squared. And because we can't say that A times B is equal to B times A for sure, right? We can't combine these. We can't. They're not like terms. So this kind of expansion doesn't work, right? Because while numbers commute, matrix multiplication doesn't. So we don't have a binomial. But there is a special case. Like, so imagine you have let's call this B plus, and you have the identity. And you raise this to the power 2, say. Well, you would get B times B, B times I times B, and then B times B. I mean I times I, sorry. Well, identity is special, right? So again, I is identity. Matrix. Because identity times any matrix is equal to itself. You have B times I is B, I times B is B, and then I squared is I, right? Identity times identity will be itself. So now we can combine these two matrices, right? You can write that as 2 times B. So as it turns out, if you have a matrix plus identity and you raise it to a power, because this is the identity, this will act very much like this where, like say, B is equal to the number 1. And there's a more general case of this where this matrix doesn't have to be identity, but rather it has to simply commute with the matrix B. But I'm just going to focus on the identity here. So as long as these two matrices commute with one another, you can combine terms. Okay. All right. So in this case, we do have a binomial theorem for this these matrices. It will be B plus I, or any other matrix that commutes with B, is the sum as k goes from 0 to n choose k, and then we're going to have b to the k, then I to the n minus k. So it very much is the same form as the binomial expansion for numbers. And we can simplify this further, right? Because we have the identity. Identity raised to whatever power is the identity. Okay. So, great. So we have this nice formula. So now we're going to use it to solve the problem. So suppose we have a matrix A. And well, first of all, I'm going to compute the A inverse just because we're going to be using it. But A inverse, well, you know how to do this. You augment matrix A with the identity and row reduce, and you would get right. So I didn't do anything special here, and I didn't do anything that you didn't do last homework. Right? I'm just augmenting this matrix with the identity and row reducing to get A inverse. Use that procedure. At least to find the inverse of A, you augment with the identity. You apply row operations until A becomes I, and this is invariably A inverse if the inverse exists. All right. So now we're going to compute A to the power 50. Now, if this were a diagonal matrix, right, then this would be easy, but it's not. So what are we going to do? Well, we're going to write it like this. B plus I raised to the power, right? N. So if I have A, and I want to write it as a matrix B plus identity, that's pretty simple. I see why the identity works really well there. I mean, we have the ones in the diagonal. And what would the matrix be? It would be just everything but the diagonal ones, right? So we would get 0, 0, 0, -1, 0, 0, 0, 2, 0. You agree that this matrix plus that identity gives you the original A. And this matrix is, well, it has a nice property. It's called the nilpotent matrix. And a nilpotent matrix B is one where if you raise it to a power, so obviously we're talking about square matrices. If you raise it to a power, eventually it'll become the zero matrix. So a nilpotent matrix B is one that if you raise to a high enough power, it's going to be the zero matrix. And let's check that this is nilpotent. We're going to define, by the way, we're going to define B to the power 0 to be an identity. B raised to the first power is just B. B squared is B times B, so let's see. Let's see. 0, 0, 0. 0, 0, 0. And then -2. 0, 0. Okay. So that's not the zero matrix quite yet. But can we imagine, well, let's do B cubed next. So B cubed is B squared times B. So I'll write down B squared. And then we write B. And we get, well, we get the zero matrix if you multiply this up. So indeed, this matrix is nilpotent because we raised it to a high enough power, we got the zero matrix. And then what would the higher powers of B be? What's B to the fourth? 0, right? Because B to the fourth would be B cubed times B, but B cubed is already the zero matrix. So zero matrix makes anything using zero matrix. So all the higher powers, right, powers greater than 2, give you the zero matrix. So you see how this is all going to pan out, right? We were able to rewrite matrix A as identity and this nilpotent matrix, and now we can apply this binomial formula for the special case when these two matrices commute. So let's do that. Okay. So we have a to the power 50 is the same as b plus I to the power of 50. So according to this formula, it's the sum as k goes from 0 to 50. 50 choose k, and then b to the power k. And let's write out a few of these. So you have when k is 0, and then k is 1, k is 2, oops, and then k is 3, continuing on the next line. Yeah, but why is it silly for me to keep writing this stuff? Obviously, we already noted that b cubed and higher powers of b are all 0, so all this stuff will go away. Right, so now we can easily compute a raised to the power of 50 because it just consists of these three terms, and we just got to multiply everything out. Apparently equal to 50 choose 0. What's 50 choose 0? I guess we should do those. I need those. These binomial coefficients. N choose 0 is always going to be 1. It's defined to be 50 factorial divided by 0 factorial divided by 50 minus 0 factorial. Well, it's 50 factorial divided by 50 factorial. It's 1. And then 50 choose 1. That's going to be 50. Let's see why. So n factorial divided by k factorial divided by n minus k factorial. Well, 50 factorial is 50 times 49 times 48 all the way through 1. So you can write that, so you can write the largest factor of 50, and then the rest of it is 49 factorial. Right? It's 50 times 49 factorial is 50 factorial. And then you have 49 factorial in the denominator, so these will cancel and you're left with 50. Also, your calculators have this function, this choose function, this combination function. Wolfram Alpha will do it for you as well if you want to check yourself. And then finally, 50 choose 2. So n factorial divided by k factorial divided by n minus k factorial. This time we would write out 50 factorial as 50 times 49 times, and the rest of the factors, you can just lump them and call that 48 factorial. 2 factorial is 2, and then 48 factorial here, we now cancels with 48 factorial on top. So we get 50 times 49 divided by 2. And okay. So a to the power of 50 is 50 choose 0. So 1 times the identity. That's b to the 0. Plus 50 choose 1. It's 50 times b. Plus this number, embarrassing numbers in the calculator. 1,225 times b squared. And b squared is right there. So that's it, right? You get 1 to the diagonal. You get negative 50. And we get 100. And over here, negative 2,450. So that's a to the power 50. Notice that if I even used higher powers, it still wouldn't have really changed too much of the problem because b cubed would still be 0, so you know it could stop there. It's just these binomial coefficients would change. Cool, so what would, let's say, a to the negative 50 be? I write a to the minus 50, I guess what I'm saying is the inverse of a raised to the power 50. Or equivalently, a to the 50 is inverted. So you have two choices. You can either repeat the procedure we did here for a inverse, right? A inverse can be written as a nilpotent matrix, and it is. Plus identity, and repeat the procedure using binomial expansion. So this is nilpotent matrix plus identity. Or you can simply take a to the 50, which we just computed and inverted. So to find the inverse of that matrix. To save time, I won't obviously go through the same procedure, but this will give you the answer. I wonder if this is a trend. Okay, I found that the inverse, this is a to the power 50, I found that its inverse is itself. Interesting. Well, I should have tried that before I came here. So I wonder if that's a pattern. Okay. But anyway. Oh, no, wait a minute. What am I doing? It's not quite itself. This turned negative 100, this turned positive 50. So there you go. It's not the same. And this became, let me double check. Right. And this became, it's not itself. It just got so close that it fooled me. Right? Like, easily fooled right there. All right. There you go. So I would just find the inverse of this matrix. Okay. So then, that's that one problem, number 3. Now let's define what is the symmetric matrices and a skew symmetric matrices. symmetric matrix is easy to recognize because you see the symmetry. If I give you an example, you'll see the symmetry. That's an example of a symmetric matrix. Right. When you see the symmetry, if you draw a line about the diagonal here, through the diagonals, you see that these entries are the same. They're kind of opposite each other like a mirror image. That's symmetric matrix. But how would you define, like mathematically, or, yeah, how would you define a symmetric matrix? Well, you define it by noting that if you know, the rows are the same as the columns in a symmetric matrix. So if you transpose this matrix A, the rows become columns. And you note that it's exactly the same matrix as A, right? Because the rows and the columns are exactly the same. So that property defines a symmetric matrix. So when they say if you have a symmetric matrix right away, you know that A transpose is equal to A. That's the very definition. And then there's the concept of a skew symmetric matrix. Here's an example. So there's a skew symmetry, right? If you draw a line through the diagonals, these are not equal to one another, but rather these kitty corner entries are negative to one another. So how would we define a skew symmetric matrix? Well, if we take the transpose of our skew symmetric matrix, do we get the original matrix? No, not quite, but close, right? We note that if you, that B transpose is -1 times B. Right, so if I start with B and I multiply everything by -1, I would get B transpose. So that's the defining property of skew symmetric matrix. The transpose of it is equal to the negative of the original matrix. Okay, is it coincidence that I wrote zeros in the diagonal? So if I use index notation, the skew symmetric matrix, the ijth entry, right, is how is it related to the jith entry? So if you take the, say the 1, 2 entry in our matrix is -1, okay. And then you look at the 2, 1 entry, it's +1. Then we see that the ijth entry has to be the negative of the jith entry. That's the way you define the skew symmetric matrix using index notation for these matrices. And so what does that say about the diagonal entries? So if I look at a diagonal entry of a skew symmetric matrix, let's say the ith entry, the ith diagonal entry, it still has to be the negative of the ith entry, right? And that's only true for what number? If let's say bring this over here by adding this to both sides, I get 2 times the ith entry is 0, therefore the diagonal entry here has to be the number 0. So in a skew symmetric matrix, the diagonals have to be 0. So now we'll have a little fun here with algebra. And we're going to show that you start with any matrix, any square matrix. You can always write it as a sum of a symmetric matrix and skew symmetric matrix. Well, maybe I should call it C. I'll just call it C so I can keep using letters A and B for symmetric and skew symmetric matrix. So we're going to take C and we're going to try to write it as a symmetric matrix plus the skew symmetric matrix. So how would we define such matrices? Is it possible? Well, we're just going to use properties of transposes to help us define these matrices. Okay, so, all right. So C we want to be equal to symmetric matrix plus skew symmetric matrix. And we want to take advantage of the defining properties of, symmetric matrix. Transpose is equal to itself. Skew symmetric matrix, transpose is equal to the negative of itself. We want to take advantage of that. So I'm just going to take the transpose of both sides, right? C transpose on the left, and then A plus B transpose on the right. And we know that by properties of transposes, the transpose of the sum is just the sum of the transposes. So that's by properties of transposes. And so what's A transpose? A. Symmetric. And B transposes the negative of B. So now we're going to take these two equations, equation 1 and 2, and we're going to add them, right? Because then we see that B minus B is going to go away. C plus C transpose is 2 times A. These double up, these add to the 0 matrix. So now we simply divide both sides by, or multiply both sides by 1/2, and there we go. Apparently, if we have a symmetric matrix, we can define it this way. And is this indeed symmetric? Well, yeah, by design, but we can directly compute it that it is. I'm just going to transpose A to make sure that it's equal to itself, to make sure that it is indeed symmetric. Transpose of a number is that number, right? And then the transpose of the sum is the sum of the transposes. And then transpose the transpose, you're back to the original. So, indeed, right? A transpose is equal to, well, this, which we define to be A. So A transpose equals A. It checks. A is a symmetric matrix if we define it in this fashion. So, what would we do to find a skew symmetric speed next? Well, we're probably going to subtract these two equations, right, from one another. Because then if we have A minus A, that A goes away and the B's will double up, and we can solve for B, or skew symmetric matrix. So now I'm going to take the two equations. I'm going to subtract one from the other. I get C minus C transpose is A minus A, that's the 0 matrix, and then get 2 B's. So we should define B to be half of C minus C transpose. And you can check that if you transpose B, you're going to get the negative of B. You're just using properties of transposes. So it's indeed skew symmetric. So this shows that indeed you start with any matrix. If you want to write it as a symmetric matrix plus skew symmetric matrix, you can do the following. Here's the symmetric matrix. We define it to be 1/2 C plus C transpose. And then the skew symmetric matrix is 1/2 C minus C transpose. Okay, so now we just have to compute these, and our job is done, right? We're expressing matrix C as the sum of symmetric matrix and skew symmetric matrix. So let's see, 1/2 matrix C plus its transpose. I'd like to see direct evidence, direct confirmation that this is going to be a symmetric matrix. Plus one-half C minus C transpose. Anyway, we get, let's see, 4 divided by 2. 4 divided by 2. 2 divided by 2. Okay. Well, okay. So this is indeed a symmetric matrix, right? And this is going to be skew symmetric, so direct computation. And that's skew symmetric. Our job is done. Okay. It's an interesting fact. Can we take advantage of it? Yeah. So we'll take advantage of this fact in the following example. We're going to be looking at quadratic forms. Nice ones like what would happen if you have this 3x1 matrix with unknowns, let's say x, y, z. You're going to multiply this by a 3x3 square matrix. Let's make it symmetric, why not? And then we're going to multiply this by the transpose of this 3x1 matrix. So this has the form x transpose times matrix A times x. Okay, now what is this going to give us? What kind of matrix? What size matrix? What size matrix does it give us? Well, let's just check, right? 1 by 1. Right? This is a 1/3 matrix. I mean, it's a transpose of 3x1 matrix. This is 3x3. So all these multiplications are defined, and at the end of the day, you get a 1x1 matrix. And so, in other words, we're going to get a number, right? And this is a number. It's going to be a formula in terms of x, y, and z, but the output nevertheless is a number. And that's, if you multiply this out, and you should, you're going to get, because we'll be seeing this again, you're going to get x squared 4xy, oh, it's x squared 4y squared 5z squared. And you're going to get the mixed terms, so 4xy, 6xz, and negative 2y. That's just a computation you would have to suffer through. And the idea, and you can reverse the process. The idea is that if you have a quadratic form like this, or the combined powers of all these terms is 2, so quadratic form. You can reverse the process and write the quadratic form in this fashion. Just x transpose ax. All right, and so, awesome. So now we're going to do the following problem. Suppose we have our matrix A, right, as before. Unfortunately, I erased what. Oh no, that's the homework problem. Crap. I don't want to do that. Sorry. And I want to find a symmetric matrix B such that the following is true. So, x transpose times A times x, to give you a quadratic form, is equal to x transpose bx for all possible 3x1 matrices. So you could do this the really long way, right? Which is actually, right, assume that B is some symmetric matrix, so you would have like B1, B2, B3, this would be B2, this would be B3, B5, B6. So the symmetric matrix is defined by 6 entries, right? Because by symmetry, you know that B2, these two numbers have to be the same, these two numbers have to be the same, and these two numbers have to be the same. So you really just have 6 unknowns in this matrix. And then you can actually multiply stuff out, right? Like, so you can reason that if this equation is to be true for all possible 3x1 matrices, it should be true for very specific 3x1 matrices. So then you can like try letting x be very simple vectors, like 1, 0, 0, or 0, 1, 0, 0, 0, 1, and so on, and even, it's probably not going to be enough, you need to try some other ones. And then you get a system of equations and unknowns where you can solve for these unknowns. Okay? You can find this matrix. But in the homework, it's suspicious that this problem is part B of the problem where we wrote any matrix as a sum of a symmetric and skew-symmetric matrix. Right? Very suspicious. So let's try to use some theory here. So if A can be expressed as a symmetric matrix plus skew-symmetric matrix, and we know it can because we found formulas for defining it. What can we say about, so let's suppose A is the symmetric matrix, A1 is the symmetric matrix, and A2 is the skew-symmetric one. what can I say about the quadratic form you get if you use a skew symmetric matrix? Now this is a number, correct? This is just some number, if you'd like, a 1-by-1 matrix. Some number. And what would happen if I transpose both sides? And I guess maybe why would I be motivated to transpose both sides? Well, take advantage of this fact, right? So I'm going to transpose both sides. And what's the transpose of a number itself? Right? It's like a transpose of a 1-by-1 matrix. And then we use properties of transposes. So we're going to the transpose of a product is just the product of the transpose split in reverse order. So you're going to get X transpose, A2 transpose, and then X transpose transpose, which gives you, of course, X. Right? Okay, and then because we know that A2 is skew symmetric, A transpose is equal to the negative of A2. So we can write that this is negative X transpose A2 X. Okay, so now we have that these are equal to one another, right? They're both equal to K. So and as often happens when something is a number is equal, well, if a number is equal to its negative, what is that number? Right. So I'll add this to both sides. This is a 0 number, right? So this itself must be 0. So as it turns out, using some theory, we see that the quadratic form where this matrix in the middle is skew symmetric always gives you 0. So we can take advantage of that fact, right? Let's take advantage of the fact. Because we want X transpose A times X to equal X transpose B. X, where B is symmetric, and we know that A can be expressed as a symmetric matrix plus skew symmetric matrix. And now we can distribute and we get X transpose A1. X plus and what do we know about this, right? A2 is a skew symmetric matrix. So the quadratic form you get by using it is 0. It just goes away, as we proved in a second. This will go away. And so now you're left with our answer. So remember, A1 is a skew symmetric matrix. So B would be A1. And how do we define, given a matrix, how do we define a symmetric matrix using it? Okay, what were the two formulas? Well, the symmetric matrix we formulated was given by 1/2 A plus A transpose. Right? That guaranteed a symmetric matrix. The skew symmetric matrix we formulated to be A2 plus, that's right, 1/2 A minus A transpose. And so this would be our symmetric matrix. So let's find it. Well, we did it a second ago. I just forget. I know what it is. It's like 2. what did we write last time? What was this? What was the symmetric part? Anyway, we just compute this, right? Write A plus A transpose and multiply by half, and we get 2. 2 to 1. So that would be our answer for D and C. And then you can confirm that that equation indeed holds if you let D be A1. Now notice that the diagonal entries are the same, and these entries are just, if you add these up, right, you get 4, and then you divide 4 by 2 to get the 2 entries here. If you add these numbers, what do you get? You get 2, so you can rewrite 2 as 1 plus 1, and this is, add these two numbers, you get 8, and 4 plus 4 is 8. So, any questions on the homework that I left out? I left out some questions that are kind of similar to stuff we've done before using triangular matrices. So what did I leave out? I essentially left out problem 2. But I think that's enough for today. Okay? Thank you.